Welcome students. In this module, we are going to discuss about momentum equation, application of momentum equation in rapidly varying flow. In module 1, we already discussed about what is meant by rapidly varying flow, RVF, rapidly varying flow. It's nothing but if I construct any dam, if flow comes out, then its depth increases rapidly. Here depth is y1, but here depth will become y2 within short distance. Within short distance, if depth of flow increases rapidly, then that is called rapidly varying flow. Since in rapidly varying flow or hydraulic jump, in rapidly varying flow or hydraulic jump, losses will be more because from y1 to y2, because of you may see in spillways means excess water to be it's a pathway which is used for removing excess water from dams. Okay, if you see at outlet of dam, you can see there will be a lot of eddies. There is a lot of eddies and whirls and currents forms at this exit point. Because of that, here there will be a huge energy loss, head loss will happen. So in rapidly varying flow or hydraulic jump problems, application of our normal Bernoulli's principle is not a good idea. So here lot of forces are involved. So momentum equation is a best thing for solving hydraulic jump problems. So now let's discuss what is momentum equation. Then we will apply the momentum equation in hydraulic jump. First, what is momentum? Momentum is nothing but okay, rho q v. Rho is density, q means discharge, v means velocity. Momentum. Okay, this is called momentum. What I am going to see, we are going to see here is very simple. As per momentum principle, if I taking this gate, here there is a lot of forces are involved. For example, first I have to draw control volume. If I am taking this control volume, what all the forces are involved? Here hydrostatic force will be here. Here also hydrostatic force due to water. Then forces from gate. Okay, so if I am taking this control volume, this is force from gate. Here water hydrostatic force. Okay, it acts at 1/3 force at due to water at BD section. Like that, here water is up to depth of full depth. So I am drawing this as force at section A C. Okay, this is force due to gate. Okay, what momentum principle says, momentum coming in x direction, here it's an entry point. Okay, this is external, all these are external forces. Okay, all these are external forces. Like that, if I take same control volume, I am taking this as control volume. Entry momentum is rho a1 v1 square. Exit momentum is rho a2 v2 square. That means here there will be velocity of v2. Here entry velocity is v1. So enter momentum is rho a1 v1 square. Exit momentum is rho a2 v2 square. If I am taking this momentum, what this is momentum coming in x direction, this is momentum going out in x direction. as per momentum, rate of change of momentum, momentum coming in x direction, I am erasing this. Momentum coming in x direction minus momentum going out in x direction should be equal to all external forces in x direction. For example, here on external force at AC, then here external force acts at this direction, so minus F of BD. Then this gate force, this also in negative x direction, so minus F of gate. This is momentum equation. This momentum equation can be applied for solving hydraulic jump problems, because in hydraulic jump problem losses will be more. Now let's derive hydraulic jump derivation. Okay, hydraulic jump derivation, and we will derive head losses in hydraulic jump also. This is the hydraulic jump diagram. In this hydraulic jump, this y1 is called depth before jump. Here at section 1, it will be supercritical. We know what is supercritical. Here fluid number will be greater than 1. At section 2, depth will be more after the jump. This is called depth after jump. Here flow will be subcritical. Its fluid number will be at 2 will be less than 1, because subcritical. Here supercritical, so fluid number will be greater than 1. Now we are going to derive a relationship between y1 and y2. Okay, now before jump depth is y1, after jump depth is y2. So what I am going to do is, first I have to draw pressure distribution diagram. Actually in hydraulic jump, pressure distribution will not be hydrostatic, but for simplification I am considering that as we are considering that as hydrostatic. So because of this pressure distribution, there will be pressure force at this section. Always pressure acts towards the surface. So PF2, I am taking this as section, this value as PF2, this value as PF1. PF1 is nothing but area of this hydrostatic pressure diagram. So here value is y1, here pressure value is gamma times y1, because at any depth pressure value will be is equal to gamma of that liquid times the depth. So area of this pressure force equal to area, its area. Its value will be, it's a triangle shape, half into gamma into y1 into y1. So it will be half into gamma y1 square. Like that, PF2 value will be equal to half into gamma into y2 square. But PF1 acts in positive x direction, PF2 acts in negative x direction. Okay, so I am erasing this. If you see, so net external forces, these are our external forces. External forces in x direction is equal to PF1 minus PF2, which will be equal to half into gamma y1 square minus half into gamma y2 square. If now I consider this control volume, entering momentum is equal to rho q times v1. v1 is velocity. Sorry, I am taking this as 1. So entry velocity as v1, so rho a q v1. Exit velocity equal to rho q v2. So momentum coming in minus going out value should be equal to all external forces. All external forces is equal to half into gamma into y1 square minus half into gamma into y2 square. So this is first basic equation. By using this equation only, we are going to solve all problems. If I substitute V1 is equal to discharged by area, area is nothing but breadth times y1, and v2 as q divided by breadth times y2, then all entire terms will become in terms of y1 and y2. If we substitute, and we know what is density is equal to sorry, unit weight is equal to g times density. If I substitute everything and if I cancel at both sides, then I will get a final equation like that: g by 2 into y2 minus y2 square minus yn square should be is equal to q means small q times v1 minus v2. Here actually a minus term will come, but plus or minus it will not influence much. Okay, after coming to this, if I this is in a square minus b square format, if I substitute as y2 minus y1 into y2 plus y1 is equal to, here I am taking as q, I am writing v is also as 1 by q by y1 minus q by y2. I know what is q is nothing but discharge per unit width, g by 2. If I simplify this, then I will get y2 square plus y1 y2 is equal to 2q square divided by g into y1. If I again write in this format, actually these derivations are already explained in PPT itself. You may go through there also. If you compare, it will be in a format of ax square plus bx plus c. For this equation, I know solution equation x equal to minus b plus or minus root of b square minus 4ac divided by 2a. Okay, here a value is 1, b value is equal to y1, c value is equal to minus 2 small q square divided by g into y1. If I substitute and solve in that equation, then I will get y2 is equal to minus y1 by 2 plus y1 root of y1 square by 4 plus 2q square divided by g into y1. Okay, so this is the general formula. Okay, if I we already know fn1, fn1 equal to v1 divided by root of g y1. I know fn1 square is equal to v1 square divided by g into y1. If I substitute, v1 is equal to q. I know what is v1. So q square divided by y1 square into g into y1. Okay. Okay, let's discuss. Before that, we discuss one more thing. If I take y1 by 2 outside here, minus 1 by 2 plus y1 by 2, because it will come as 1 plus, because of this y1 square, here value will become 4 divided by y1 square into 2q square by gy1. If you check, you will get idea, because if I multiply this 4y1 square here, then only this if I get inside, and if I multiply, these both terms will cancel. So minus y1 by 2 plus y1 by 2 into root of 1 plus 8 q square divided by g y1 cube. Okay, if you look here, it will be, I can substitute this. This is nothing but fruit number 1 square. So final equation will be y1 is equal to y1 by 2 minus 1 plus root of 1 plus 8 fn1 square. Like that, y1 is equal to y2 by 2 into minus 1 plus root of 1 plus 8 fn2 square. Actually, this derivation already explained in slide itself. You may go through there also, because there steps will be given. Here I am giving how the derivation is came. Okay, next we will derive head loss in hydraulic jump derivation. In hydraulic jumps, at section 1, yeah, specific energy will be is equal to y1 plus v1 square by 2g. At section 2, specific energy will be equal to y2 plus v2 square by 2g. There will be a loss due to eddies. So E1 minus E2 will be is equal to head loss in hydraulic jump. Okay, after we know E1 minus E2 is equal to head loss head loss of hydraulic jump, then head loss is equal to Y1, okay, plus V1 square by 2G minus y2 minus v2 square by 2g. Here I am taking v1 square by 2g minus v2 square by 2g in one side, minus of y2 minus y1 in another side. Okay, I can write v in terms of discharge. If I write v in terms of discharge, q square divided by 2g y1 square minus q square divided by 2g y2 square minus y2 minus y1. If I take q square outside and 2g outside, then I will get 1 by y1 square minus 1 by y2 square minus of y2 minus y1. Okay, if I simplify this, okay, this comes under a plus b into a minus format. Okay, in this equation, we already in hydraulic jump equation itself, we saw y2 square, because by solving this equation only, we got our answer. 2q square, here q square, okay, I missed q square. 2q square divided by gy1. If we take here, if we compare, if we calculate q square is equal to from here g into y by 2 into y2 square plus y1 y2. If I substitute q value as this in this equation and solve, I will get head loss is equal to g into y1 y2 by 2 y2 plus y1 by 2g into y2 minus y1 into y2 plus y1 divided by y1 square y2 square minus y2 minus y1. If I solve, if I take this y2 minus y1 outside, then I will get okay, first because of lack of space and timing, I am just simplifying this, but for all this for all these derivations are already given in slide itself. So if I put and solve once again, then I will get y2 minus y1 into, okay, here what actually here there will be square, okay, here there will be square. If I this is in a plus b the whole square format. If I write as a square plus b square plus 2ab, and if I solve y1 y2 square plus y1 square minus 2y1 y2 divided by 4y1 y2, this form is as a minus b the whole square form. So I am writing y2 minus y1 into y2 minus y1 the whole square divided by 4 y1 y2. So this will become y2 minus y1 because whole cube divided by 4 into y1 y2. This is head loss in hydraulic jump. So far we discussed about what is mean by momentum equation. Then we applied that momentum equation hydraulic jump depth calculations. Then we also used that momentum equation in hydraulic jumps and hydraulic jump derivation in head loss of hydraulic jump. Okay, thank you.